Hello, Dr. Giadi. Yeah.
Hey, hello, Dr. Grace.
Hi. Yeah. It's Grace. Yeah. How are you?
Good, how are you? Pretty
Yeah.
good.
Fine. Yeah.
Yeah,
So, thank you for accepting the invitation.
yeah,
Please
thank you.
convey my regards to Dr. Srihari as well.
Yeah, thank you. It's really
Thank you.
nice to meet you here.
Yeah. So for today's session, Dr. Vimala, she'll be the chair of the session, introducing you. And after she introduces you, you can share your presentation and put it in presentation mode. Yeah. Would that be
Okay, for
fine?
sure.
Yeah.
Thank
Perfect.
you. Thank
Yeah.
you, Dr. Vimana. Thank you.
George sir, give permission to share the screen. Professor George.
Hello? Yeah.
Yes.
Good evening, Jia Ding. It's my pleasure to introduce you for today's session.
Thank you.
Dear participants, we have the next speaker, Dr. Jia Ding. The topic of his speech will be vibration and heat assisted atomic force microscope based nano machining. Dr. Jia Ding joined the Department of System Science and Industrial Engineering at Binghamton University as an assistant professor in 2017. In 2013, he received a MS degree in mechatronics engineering from Huazhong University of Science and Technology, Wuhan, China. In 2017, he earned his PhD in industrial engineering from North Carolina State University, Raleigh, North Carolina. His research interests include process innovations and applications of AFM-based nano manufacturing and additive manufacturing in biomedical fields. Now, I request Dr. Jia Ding to deliver his lecture.
Sure. Thank you very much for your introduction, Dr. Vimala. So shall I share screen right now?
Yeah, you can share.
Okay. So can you see that?
Yeah, we can see your slide.
Okay. I'll get started. Good day, everyone. So it's my pleasure to be here and to present my research topic. So today I'm going to talk about vibration and heat-assisted atomic force microscope-based nanomachining. So first of all, the agenda, I'm going to talk about introduction. So that will include many existing nanomanufacturing techniques. And later on, after that, I'll talk about vibration-assisted atomic force microscope, in short, AFM-based nanomachining. And it will include setup, the mechanism, and results. And also, I will talk about the vibration and heat, both using two different energies and integrate them together. And the vibration and heat-assisted atomic force microscope, in short, AFM-based nanomachining. It will include also setup, mechanism, and results. So first of all, I would like to have a quick introduction about the nano manufacturing. So the nano manufacturing, it is the manufacture of sub 100 nanometer patterns, components, devices, and systems. So it is the fundamental for many applications, including the chemical sensors, the energy storage, semiconductor industry, optical, biomedical, and many research and development. So as for very specific applications, it can be divided into like 2D and 3D nanostructure applications. So so most of the two-dimensional nanostructures, as we know, are, for example, photolithography chips for the CPU fabrications. And for 3D nanostructures, we can see here, we have optics. So optics showing here is a focusing lens. This one is fabricated by the focused ion beam, and it has a few micron diameter, And the function is to get the laser focused from 5 micron diameter into 1 micron diameter. So so this one can be directly nano imprinted on a single mode fiber, laser fiber. And besides the optics, some 2-dimensional and 3-dimensional nanostructures can be applied on plasmatics devices and bio nano devices such as nanofluidic channels. For example, this specific application shows the nanofluidic channels with 10 nanometer channel size. So the DNAs, RNAs can be going through, filtered through, and so this one also shows some nano patterns. So with all those applications on the nanometer scale, we need the fundamental nanofabrication techniques to implement those applications. So the existing nanofabrication techniques, including first extreme ultraviolet EUV and X-ray lithography, and also the very common one is electron beam lithography. Besides, we have ion beam lithography and atomic force microscope, AFM-based nanolithography. So I will have a brief introduction of each. So first is EUV, the extreme ultraviolet lithography. So this one is a next generation nanolithography technique for the CPU, for the sub 5 nanometer nano feature size fabrication, such as next generation CPU. And the machine, so of course it is very advanced. It is a cutting edge, but there is a limitation showing up here. Obviously, is it can only be, this machine is can only be fabricated by ASML. Okay, only in the world, throughout the world, only one company can fabricate this machine, and this EUV machine will cost about $1 billion. Okay, 1 billion. So so all the big semiconductor manufacturers will have to buy this if they want to advance their nanofabrication factories. So besides the EUV, we also have the electron and ion beam lithography. So for the electron and ion beam lithography, they use electron beams to directly touch on a sample surface and then generate the patterns. So for the commonly used the photolithography masks, they usually fabricated by electron beam lithography. So for the electron beam lithography and ion beam lithography, it is also very good, useful for fabricate arbitrary patterns, because this is a maskless nanofabrication technique. So the masks fabricated by this electron beam and ion beam lithography, they can be used for photolithography to fabricate CPUs and IC chips and some other patterns. Of course, it has its own limitations. So that includes the scattering effects and difficult to fabricate 3D patterns, expensive, etc. So I have a brief explanation for this limitation. First of all, let's take a look at this upper left corner picture. It shows the scattering effect if we have electron or ion beam scattering on the substrate and the sample. So usually the photoresist. So let's assume this is the zero is the zero and underneath are the photoresist. When the electrons or ion beam have a contact in a sample, because the electron is very light and it has a tendency to interact with the substrate, and then it can be easily be scattered. And so that results in larger dimensions. And also, because of this very specific characteristics, so we can see when we have 3D patterning needs, it is not easy to fabricate, and it will have generated many difficulties and limitations. So for electron and ion beam, there's overview, a simulation over here, different energy and different sources will have generated different patterns over here. As you can see, because of the electrons and the ions, ion is much heavier than electrons, but it also has some substrate damage potential issues over here. So for the AFM-based nanomanufacturing, there are so many existing techniques has been developed, such as mechanical direct scratching, dynamic plowing, and thermomechanical material removing, and the electrostatic nanolithography, etc. So I have two quick example here. First is direct mechanical scratching. So as we can see, the AFM atomic force microscope, originally it has been used as an image tool, but because for the AFM, well, where it's doing the imaging, the cantilever has intermittent contact with the surface. So that means there is a small, even very tiny, the small force have interaction between the AFM cantilever and the sample. So the previous researcher was wondering if they can really apply larger force so they can fabricate patterns on it. And then this is a mechanical direct scratching. You can imagine this is a CNC, like a traditional CNC manufacturing is in a nanometer scale. And another thing is the electrostatic nanolithography or VCAN. So this image shows using the electrostatic force. So the water meniscus between the AFM tip and the conductive substrate has can generate a semiconductor patterns on this. So we talk about the common nanolithography techniques. So what are the pros and cons over here? So we talk about EUV and X-ray. So for the extreme ultraviolet, it has a high throughput because it's for industry. It's very high resolution, sub 5 nanometers. However, it is very expensive, right? And not able to easily make 3D patterns. And 3D electron beam and ion beam lithography. So they are maskless fabrication techniques. It's very high resolution. And however, as we mentioned, it has electron beam scattering and expensive, and ion beam has extensive substrate damage, etc. So the traditional AFM-based techniques, as we just discussed, it is because atomic force microscope, it is not as expensive as UV machine, is not as expensive as electron beam and the ion beam lithography machine. So it is quite cost effective, and it is kind of easy to set up. It doesn't require very high vacuum. So it also has a comparable resolution comparing with the electron beam lithography. However, for the mechanical direct scratching, as you can see, the general original idea is to using very large normal force and generate quick tip wear because of large force. So because the tip wear has a positive relationship with the normal force. And then it has, because using a single tip, very tiny tip, and at the end of the AFM, so it has a very low throughput. So those are some existing limitations. Therefore, we introduced the vibration-assisted AFM-based nanomachining techniques to overcome those limitations for existing AFM-based nanomanufacturing. Okay, so first I'm going to talk about the experimental setup and of the vibration-only assisted AFM-based nanomachining. And following up, I will talk about vibration and heat assisted AFM-based nanomachining. So I include both the vibration and heat. So first is the vibration only. So as you can see for the experimental setup, the traditional or commercially available AFM is the outside illustration here. And this is a cantilever. And the core part here to generate the vibration we mentioned here is the nano vibrator here. So the nano vibrator has a X piezo, Y piezo, and a Z piezo. So each piezo are driven by sinusoid signals. We'll discuss the mechanism later on. So the AFM tip we use is a tap 190 DLC. So it is very stiff AFM probe with the spring constant 48 Newton per meter. We're going to discuss those spring constant later on too. So the input XY signals with sinusoid of 2 kilohertz over here. So it will has 90 phase differences. So it will generate a circle where the piezo has a pushing and pulling, so it will generate a circle over here in XY plane. And besides that, the Z piezo will have input signal with ultrasonic vibration with 2 megahertz. So specifically for the XY vibration and the Z vibration, the mechanism is like this. When we apply the XY vibration, so that means when we apply signals to generate the pull and pull signals in terms of the implant, there will be a virtual tool forms. So this is the illustration that shows the virtual nanomachining with XY vibration. So as you can see, at the very beginning, if we only have the traditional AFM tip, it is going to have a very tiny piece of point over here. That means when we have a one single machine pass, and it will the trench size will be the same as the tip size. However, if we have XY vibration, the overall radius or the trench size, it is a combination of the vibration amplitude as well as the tip size. So that is a function of the XY vibration. It can help tune the size of each nanomachining trenches. So for the Z vibration, in the Z vibration, the function is to dynamically freeze the cantilever. So the cantilever can be easily indented into the surface. So as we know, if the substrate vibration has very low frequency and we're working, so the AFM tip will vibrate along with the Z vibration. So the tip will not easily indent into the surface, and that's not easy to generate patterns, of course. And because of the ultrasonic vibration frequency, and the AFM tip is not able to reflect or move or vibrate along with the Z vibration. Therefore, the AFM tip can indent into the sample surface over here. So that can easily generate different depths of the nanostructures. So let me show the nanomachining capabilities with the vibration, okay? So first, we'll talk about the capability. If we include the XY vibration into this nanomachining setup. So as we can see, this is a vibration, the XY vibration effect. As we can see, if we increase the amplitude of the vibration implant, we can directly increase the nanomachining trench width from 4 nanometer to 35 all the way to 100. Of course, we can go even larger because we can easily tune the input vibration amplitude. Therefore, we can control the width of the nano trenches. And besides the XY, and we also have the control of the Z vibration. So as we can see, if we increase the Z vibration amplitude from a certain point to a larger value, we can see the actual depth. This is actual depth, and this is a design depth. For all the experiments, we designed 20 nanometer depths, and with 1.5 volts of the Z vibration, it is a little bit smaller than 20. And while we're increasing the vibration amplitude in the Z direction, as we can see, the depth actually get increased. So that means if we can fix a Z vibration amplitude. So in this case, we fix it at 2.5 volts. So there will be a constant gap between the designed depth and the actual depth. So in that way, we can just simply design by considering this actual differences. As you can see, we design the depth from very small values. Here's 10, 20, 30, 40, 50, 60 nanometers. So with the 2.5 volts Z vibration, and there's a constant gap between the design ones and actual ones. So in that way, we can control the depth in the Z direction. So in that way, we can make a 3D geometries, 3D patterns, not only 2D. So therefore, this is a quick example shows the capability using this experimental setup, we can get the IC patterns over here. And if you want to know more details, you can search this paper here. So we talk about so many. We talk about the basic mechanism and so many advantages over here. And I want to implement a little bit more about the AFM-based 3D nanomachining advantages. And so first is when we fabricate 3D patterns, which is not easy to be fabricated by other techniques. So the AFM has a cantilever or tip, as we just mentioned. So tip looks like this in SEM. So this is actual image, and it has a positive draft angle. So that means if we have a tip that can be used to remove materials, substrate materials, and it will generate a natural draft angle. So that means this can be easily demolded if we put some materials and use the pattern as the mold, right? So this is a very good characteristics of the AFM-based 3D nanomachining technique. And besides, of course, easy to set up and low cost, etc. So as we can see, because of the possibility of using this AFM-based nanomodes as the mode, to we can fabricate subsequent daughter modes and then uses parallel manufacturing other than the series. So as we can see, the application here, for example, we can easily fabricate 4 identical structures using the vibration-assisted AFM-based nanomachining. So as you can see, the 4 identical 3D nanomodes, as we can see, this is the design pattern. This is AFM results directly from image. And this is the underneath picture shows the cross-sectional profile of the first layer and all 3 layers. Okay, so we can see clearly 3D patterns can be fabricated with very good structure fidelity. So we just talk about AFM cantilever tip has the capability of getting the positive draft angle. So when we pour in the PDMS soft materials, we can easily demold and get a reverse the nano patterns structures in 3D shape. So the reason we use the 3D nanomachine patterns as a mold and to use the PDMS material as a soft stem to fabricate this is we can see AFM, just like the electron beam and ion beam lithography techniques. It is a serious fabrication process. So we're trying to make it scalable and maybe even in a quicker way, in a more efficient way. We can use a PDM stamp. So we have a stamp, we can easily stamp them into a just like we do in a parallel way. So this is one example, and it shows it can fabricate PDMS in a reverse way. And I also attached a few other examples here. This is the logo using AFM-based nanomachining and the PMMA surface, of course. And it has a different depth, showing a different Z height features. So doing the same thing, we use the PDMS soft stamps, soft materials. We do the casting, and we fabricate the reverse geometry like this. As you can see clearly, different Z heights with clear resolutions can be reversely fabricated. So after we get the 3D nanomodes, we can do the printing, as we just mentioned, instead of machining those 3D structures one by one. And then in that way, we can provide more higher efficiency, right? So as we can see here, the PM coating is the material that we do the nanomachining as well as the following fabrication. The coating is on a substrate, and then we use the 3D nanomachining techniques, as we just mentioned. And then reversely, we generate the PDMS, as we just showed. So after we get the PDMS mode or stamp, so we can use the daughter mode or stamp to contact imprints. So there will be the liquid or solvents that can solve the PMMA coating or some substrate coating. So we usually use the acetone here or anything. So any organic solvent can be used here. So usually it's acetone. So after doing the contact imprint, so we can duplicate the PDMS stamp pattern on the new coated PMMA surface. In that way, we can efficiently fabricate the 3D nanostructures using the PMS mode. So we call this entire process as a solvent-assisted micro molding process. So so here I'm going to show some results. The overall shape and different layers are shown by here. As we can see, because of this is a manual, I tested out using a manual process, and then it shows not as good as the original nanomachining process results using AFM, but it's quick. It shows clearly a few layers, and the entire feature around the 20 to 40 nanometer, less than original total depth of 80 nanometer. And it is a subsequent application for stamping fast in a different substrates. So this result is, you can read more by searching this paper here. So we talk about a lot of three-dimensional. This is another one. We talk about a lot of applications or capabilities of the vibration-assisted AFM-based nanomachining. So as we can see, this is another example. We have the original pattern. We have the AFM-based nanomachining pattern, and we overlap the measurements to compare the nanomachining quality using vibration-assisted nanomachining. So as we can clearly see, this is a dotted line. Dotted line shows the original pattern. So those are the original traces, and the solid line are results from the AFM-based nanomachining to duplicate that original pattern. As we can see, a lot of details has been lost because of these tiny unmatched areas. You see, so there are so many reasons to generate this tiny unmatched areas. One reason is some vibration and some sharp angle, because this is almost, as you can see, this is almost a 90-degree vertical wells. We cannot easily use a AFM tip to penetrate into to get a vertical wall, as I just discussed before, because it has a positive draft angle naturally. So, and besides all those natural reasons, there is another reason we need to consider. That is the tip wear. Because of the tip wear, so we cannot machine many 3D patterns in the same fidelity or in the same quality, because the tip is going to gradually wear because of even though we add the vibration in the X, Y, and Z vibration direction, it will still cause the tip wear. And we cannot manufacture this tip jobs for like 20 or 30 patterns without fidelity degradation. No, just simply it will cause the tip wear. So we're thinking about reducing the force when we're doing the nano manufacturing, right? So before doing that, I want to introduce a little bit about the literature again. So the heat-assisted AFM-based nanomachining. So when we think about how can we reduce the force, we naturally think about a heat-assisted AFM-based nano manufacturing. First is because the sample. Second is because the heat usually doesn't use too much force because of the heat. So let's talk about this, and we come back to the vibration heat-assisted AFM base. So there are some existing techniques over here using the pure heat. Only the heat is applied on the AFM-based nanomachining. So first is there are two techniques. First is apply heat through the AFM tip The second is apply heat directly on the sample. So we can see when we apply the heat directly through the tip, and we need a very high temperature, even above 300 degrees C on the tip. So we can get some nanomachining patterning. So it's not only the indentation, because this is two regions. Okay, the upper region is the patterning. That means higher temperature, and from 100 nanonewton to about 600 nanonewton to get patterns. And then if you don't need the patterns, the consecutive patterns, you can use you only need the indentation, just like an IBM mini pad project, like fabricating the memories. Those only need the indentation. It doesn't need that much high temperature. So, but still needs that high force. So this paper is published on Science 2010. So it shows a very good, promising technique using the heat as a technique to do AFM-based nanomachining. Okay, and besides, there's another technique showing apply heat on a sample. So on a sample, it shows only 40 degrees C. We can do some nanomachining on it with only about 50 nanonewton. So this is a paper. This is a paper from Micron. So published on Micron. So but however, we can barely see any patterns. So just because of the substrate temperature increase, and there are some certain limitations, it has not good quality. So then we're trying to say, okay, because our vibration has that much capability, can we incorporate the vibration and heat together to get better results, comparing with only applying the vibration or only apply the heat? Because for only apply vibration, the tip wear is an issue, right? And if you only apply the heat, you can see, we just talk about those limitations. So then we innovate and integrated a heating element in our vibration-assisted AFM-based nanomachining setup. Therefore, we have the setup here. We can see the same vibration, X, Y, and vibration. This time we kind of save the Z vibration here. And then we apply the heating element here. So there's temperature can be applied on a sample. And those are the outside is a commercial AFM. So tip we use this time is smaller spring constant, quite smaller than the previous vibration assisted process. We're going to talk about this later on. And the substrate is PMMA. And temperature is, when we do the experiments, it's around 25 to 45 degrees C. So what is good about vibration when we apply it on the heat assisted? Or what is good about heat when we apply it to the vibration assisted? So as we know, when the heating energy or temperature get increased on the substrate, there will be some adhesion force between the tip and the substrate, because more heat and more the thermoplastic PMMA will get kind of sticky or melty. So as we can see, the AFM can, so the adhesion force can be represented by the force distance curve, which is a common curve that can be get by any AFM. So the B and C distance shows the adhesion force between the AFM tip and the substrate. So actually, we did experiments comparing different temperatures and the adhesion force between without vibration and with vibration. So this is without any vibration. This is with vibration. So we can clearly see with vibration, the adhesion force get decreased and increasing, as we can see, increasing from 30 degrees C to 45 degrees C. The adhesion force got increased a little bit, but if we apply the vibration here, the adhesion force keeps kind of consistent or even lower a little bit. And then there is a adhesion force difference between with vibration and without vibration. This is a trend showing if we have a higher surface temperature, if we apply the vibration, it will have the larger gap between the adhesion force. So because of the myriad integration of these two external energy, so we applied the different forces. We design a experiment, two level forces, two level vibrations with a constant sample temperature is 40 degrees C. So as you can see, using the almost 170 nanonewton and 340 nanonewton, we can see the trenches. We can fabricate very clear trenches, and not only the indentation with about 10 nanometers around using the small temperature, small vibration amplitude, and a little bit larger depths. So this result can be found on this paper published in Manufacturing Letters. So with all those interests, we want to know why we cannot use the Steve probe, because at the very beginning we try to use the same probe as we used for the vibration only assisted nano manufacturing process. But it turns out the trenches get very deep because the PMMA is becoming soft with the elevated temperature. So we designed experiments to see how the probe actually affects the features. And we designed a 2-level factorial design with 2 factors. Factor one is probe spring constant, one is a very soft probe, and one is a very stiff probe. And then we design 2 different surface temperatures, 35 degrees C and 42. And the probe is, the most important thing is the spring constant here. Those are some other characteristics here. So the input parameters, when we use the probe very small, with a very small spring constant, a soft probe. So if we use 50 nanonewton normal force, as you may notice, 50 nanonewton is a very, very small force that almost cannot be implemented by any other AFM-based nanomachine techniques. So as to our best knowledge, we can do this in the even 50 nanonewton, and we can also do that with about the 10 nanonewton if we use Steve's constant. So this is our advance in this AFM-based process. So let's see the results. If you're using 35 degrees C and 42 degrees C, so the temperature shows clearly if we use a little bit higher temperature, so we use a very small force, we can get trenches. So if we don't use a little bit higher temperature, we cannot get these trenches. As you can see, 35 degrees C, we can only get a few marks on the surface. It's not even any trenches, not clear. So if you use very stiff probe and 48 Newton per meter spring constant, same force, same 59 Newton, and same speed, same temperature, we can see very, very deep structures over here. So this is 35 and 42 is even deeper. So we actually plot this results together. So as you can see, these 2 lines shows the depth of using the small softer probes, and these very deep structures shows to using the TAP 190 DLC probe, and is very stiff probe. So as you can see, using all the other machining speed, force, with the same conditions, the cantilever spring constant actually plays a very important role here. So we do the factorial analysis of this. We can clearly see the result is there is a very significant, statistically significant results for the cantilever type and the temperature, and also it is statistically significant for the interaction between the tip and the temperature. Okay, so that means if we choose another tip, the existing the temperature selection is affected. Okay, and so if you want to see more, you can find more results on the Procedure Manufacturing is impressed. So in summary, so we just talk about vibration only assisted AFM-based nanomachining. It is pretty effective in fabricating both 2D and 3D nanostructures that can be potentially used for many applications, as we mentioned above at the very front end. And also vibration can enhance nanomachining rate and capability. And the vibration amplitude has major impact on both the width and the depth dimensions. So based on the consideration or concerns of a tip wear, we innovated and demonstrated the effectiveness of the vibration and heat-assisted AFM-based nanomachining approach to fabricate 3D or 2D nanopatterns using very small force, very small, to 10 10 nanonewton, 50 nanonewton level, and the very good results, as you can see. And also the adhesion force will decrease due to vibration. And we can, even we apply the sample heating, we can generate very good nano trenches, not discontinued dots. So, and also we dig into a little bit more. We're trying to figure out the probe type, how the probe type and surface temperature, how they interact with each other. And we did the design experiments, we do the ANOVA analysis. It shows both of them, both of the probe type and surface temperature have a great impact on the nanomachining results. And they do have an interaction in terms of statistical analysis. And thank you everyone for your attention and time. And I would like to take questions for now.
Thank you, Dr. Jiadeng.
Thank you.
I'd like to summarize a few questions which were posted by the audience.
Mm-hmm.
The first question has been raised by Dr. Gargi Rena. What is the relation between the resonant frequency of the tip in comparison with the frequency at which the sample is vibrated, which is going to be nanomachined? Yeah.
Okay, thanks for your question. So in terms of the frequency relationship here, the XY vibration frequency doesn't affect too much about the results. The only capability is to tune the width. So if we can apply the nanomachining frequency in about the 2 kHz, it can very good coordinate with the machining speed. So in that way, for each machining circle, you can only slice about 1 nanometer in terms of the machining direction. So it will have a smaller machining load for each vibration. So the vibration frequency in XY vibration will share the load when the FM is doing the machining. So if higher fabrication, theoretically, so the FM can use a higher speed to do nanomachining. However, there are some redundant vibration there, because if the vibration is keep doing the vibration, and there might be some the tip wear associated. And in terms of Z vibration, the frequency in the Z direction is very important for the cantilever. So the mechanism here is if we use a very high ultrasonic vibration frequency, so that is about the 2 megahertz range, and it is way much higher than the cantilever tip frequency, because the resonant frequency of the cantilever is about 160 kilohertz. So if we have to use much higher vibration frequency in Z direction to make the tip indent into the surface. So in that we can make a 3D structures. Otherwise, it's only a 2D, cannot change too much. Thank you.
Yeah, as a continuation of the previous question, how was the decoupling achieved between the two?
Yeah, so this is the XY and the Z. So the XY and the Z direction are decoupled naturally. So you can see XY is placed in plane, and it's going to vibrate in plane. It's going to generate a circle, and the Z direction is in the Z. So they are decoupled naturally. So the Z direction only generates the vibration in the Z direction. If you want to tune in the Z direction, it is only control the depths over there. And XY is tuning the width. Is that the answer to your question?
So the next question, how long will one DLC tip last for the nanomachining process?
Yeah, very good question. Which one improve the lifetime, of course. So typically, based on my experience, it lasts about 20 patents of the Steve Jobs, something around that. And of course, it's going to gradually degrade the tip fidelity or the tip quality. So that means the following patents will not be as sharp as the first patent. So that is a TAP 190 DLC tip.
Next, I have one more question raised by Dr. Ramesh Tamankar. It looks like the Z piezo has good resolution, but in the lateral dimensions, what is the resolution you achieve?
Sorry, can you say, so the resolution in which direction?
Yeah, it looks like the Z piezo has good resolution.
Mm-hmm.
But in the lateral dimension, what is the resolution you achieve?
Okay, so yes, in the Z vibration, it can has a good resolution, and the XY vibration, it also has like a smooth, very smooth resolution achieved. As you can see, the resolution depends on two things. One is the tip vibration, and another is the tip size. So the vibration amplitude can be tuned from 0 to all the way to about a few hundred nanometers. So it depends on, so it's a trade-off between the resolution and your nanomachining efficiency. If you're on a high resolution, you lower down the vibration of the XY implant vibration. So that means the actual tool size, the virtual tool size is only the tip size plus the vibration amplitude. If you want a high efficiency, if you want to create a trench, very wide trench with one machining path, so you can increase the vibration amplitude. So the resolution is, the ultimate resolution is the AFM tip size plus a little bit of XY vibration, if you want to say it.
Thank you, Dr. Jia, for your patient answering.
Thank you.
Thank you once again for accepting our invitation.
Thank you everyone.
Thank you, Dr. Jia. It was a nice, interesting talk. Yeah.
Thank you.
Yeah.
Thank you very much.
So George,
We can leave the session and then come back again.